Something is wrong with the early universe. Not wrong in the way a calculation is wrong, or a model needs adjusting at the margins. Wrong in the way that makes career physicists go quiet in seminar rooms, stare at their data for the fourth consecutive hour, and say, in the careful, hedged, professionally guarded language of people who spent decades learning not to overstate things, that they genuinely do not know what they are looking at. What is it? A galaxy that should not exist, a molecule that should not be there, a cosmic object so unlike anything in our catalogue of the universe that the team who discovered it named it with a word they had never used in an academic paper before. A miracle. And here is what makes this not hyperbole, not the breathless shorthand of a headline writer filling column inches at midnight. These are the findings of the James Webb Space Telescope, the most powerful astronomical instrument humanity has ever constructed, operated by the most rigorous scientific institutions on Earth, peer-reviewed and published, and still, without a complete explanation. I'm your narrator. And for the next hour or so, I want to take you somewhere that very few people have been, not just to the discoveries themselves, but into the questions that survive them. Because James Webb did not give us answers. It gave us something rarer, and in its own way, far more precious. It gave us better questions, and the best ones, the ones that keep the lights on late in observatories from Baltimore to Cambridge, do not yet have answers at all. We are going to talk about the light that left a galaxy 280 million years after the universe began. We are going to talk about a world 124 light-years away where something, and we do not know what, is generating a gas that on Earth has only ever been produced by living things. And we are going to talk about small red dots scattered across the deep field of the infant cosmos that behave in ways that no known object in the history of astrophysics has ever behaved before, somewhere in these three threads, and I suspect this the moment I will remember if any of them resolves cleanly in my lifetime, is the outline of a new cosmology, a new picture of what the universe is, what it contains, and whether it contains us alone. We are not there yet, but we are closer than we have ever been. And the journey there begins with a telescope, a mirror the width of a tennis court, and a piece of data that stopped astronomers mid-sentence. To understand what James Webb found, you first need to understand what James Webb is, not in the abstract, enthusiastic way that press releases describe it, transformative, revolutionary, and so on, but in the precise, physical, almost biological way that helps you feel what it actually means to see with this machine. The James Webb Space Telescope has a primary mirror measuring 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments, arranged into a honeycomb that unfurled like a mechanical flower after launch. It orbits not around the Earth, but around a gravitational balance point in deep space called the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, always on the night side of our planet, always facing away from the Sun. That remove, the temperature of its coldest instruments drops to minus 233 degrees Celsius. That is approximately 40 degrees above absolute zero. The temperature at which quantum mechanics itself starts to run out of meaningful predictions about molecular motion. Why so cold? Because James Webb is an infrared telescope. It does not see visible light the way your eyes do. It sees heat, it sees the long, lazy, redshifted waves of infrared radiation that carry information from the most distant objects in the universe, photons that left their source billions of years ago and have been stretched by the expansion of space itself into wavelengths too long for human eyes or any previous space telescope to resolve. To detect those photons without being blinded by its own thermal glow, the telescope must be colder than almost anything in the natural solar system. This is the engineering paradox at the heart of Webb. To see the coldest, most ancient light in the universe, we built one of the coldest, most precisely calibrated machines our civilization has ever produced. The sun shield that keeps Webb's instruments at those temperatures is the size of a tennis court, a 5-layer membrane of Captain Foil that reduces the thermal energy passing through it by a factor of 1 million. 1 million, not a typo. The difference in temperature between the sun-facing side of that shield and the instrument side is roughly the same as the difference between the surface of the Sun and the surface of Pluto. Webb launched on Christmas Day 2021. I will admit something about that launch that still strikes me when I think about it. 344 individual single-point failures had been identified by engineers in the weeks before deployment. Any one of them could have ended the mission entirely. The telescope's 18 mirror segments had to unfurl and align to within 50 nanometers of precision, the width of a human hair divided by 1,000. The sunshield had to deploy across 29 distinct tensioning cables without snagging. And all of this happened while the telescope was already 300,000 kilometers from Earth, well beyond the reach of any repair mission. We built a $10 billion instrument and then let it go. Every single deployment step worked, which, given those odds, is itself something that deserves a moment of quiet acknowledgement. But why does Webb see so much further than anything before it? The answer lies in a property of the universe so counterintuitive that most people, when they hear it for the first time, assume they have misunderstood. The universe is expanding, not just locally, not just in some regions, but everywhere, simultaneously. Every point in space is moving away from every other point, like raisins in a rising loaf of bread. The further away an object is, the faster it appears to recede from us, and this recession stretches the light that the object emits. Visible light from a very distant galaxy arrives at our instruments as infrared radiation, dramatically shifted toward longer wavelengths. The further the galaxy, the more extreme the shift. This is what cosmologists call redshift. And the James Webb Space Telescope was designed, from the ground up, to read it, where its predecessor, the Hubble Space Telescope, was tuned primarily to visible and near-ultraviolet wavelengths, magnificent for studying the middle universe, the cosmos as it was a few billion years ago. Webb is tuned to the infrared, which means it can peer through the cosmic veil and see objects in the very first chapter of time. Objects that formed not billions of years after the Big Bang, but hundreds of millions. Before Webb, the earliest confirmed galaxy we had ever observed dated to roughly 400 million years after the Big Bang. That was the frontier, the oldest thing we had ever seen, and it was already astonishing, and it was already raising uncomfortable questions about how quickly structures of that scale could have assembled from the fog of the early universe. Then Webb looked up, and what it found broke the frontier entirely. But before we get there, before we talk about MOM-Z14 and GLIMP-C7775 and the name Cosmic Miracle appearing in a peer-reviewed paper, we need to understand what astronomers expected to find, because the surprise is only legible against the backdrop of the expectation. And the expectation, in early 2022, was one of the most successful and carefully constructed theoretical frameworks in the history of science. It was called Lambda CDM, and as Webb began returning data, it started putting it under extraordinary pressure. Lambda CDM is not a catchy name. It is the sort of name that sounds like a printer error or a model number for industrial machinery, but it is the standard model of cosmology, the theoretical framework that describes how the universe began, how it evolved, and what it is made of. And for about 3 decades before James Webb launched, it worked extraordinarily well. The lambda stands for the cosmological constant, Einstein's term for dark energy, the mysterious force driving the accelerating expansion of the universe. The CDM stands for cold dark matter, the invisible gravitational scaffolding that, according to our models, makes up approximately 26.8% of the total energy content of the cosmos. Ordinary matter, everything you have ever touched, seen, burned, eaten, or built from, constitutes only 4.9%. The rest, that remaining 68.3%, is dark energy. Lambda CDM makes specific predictions. It predicts how fast the universe expands. It predicts the large-scale structure of the cosmic web, the sheets and filaments of galaxies that span hundreds of millions of light-years, with vast empty voids between them. It predicts the temperature fluctuations in the cosmic microwave background, the faint thermal afterglow of the Big Bang that permeates all of space. and it predicts these fluctuations with extraordinary precision. The Planck satellite, which mapped that microwave background to resolution of parts per million, found that lambda CDM matched its measurements to within fractions of a percent. This is, I want to be precise about this, one of the most successful predictive frameworks in the history of human science. Not pretty good, not adequate, extraordinarily, quantitatively, mind-bendingly successful, and yet, lambda CDM also makes predictions about the early universe, about how quickly structures, halos of dark matter, and within them, galaxies, could form and grow in the immediate aftermath of the Big Bang. These predictions are not vague, they are mathematically explicit. In the first few 100 million years of cosmic time, the universe was hot, dense, and relatively smooth. Dark matter halos could begin collapsing gravitationally, and within those halos, gas could cool, condense, and ignite into the first stars. But this process takes time. It is constrained by physics, by the rate at which gravity can operate, by the time required for gas clouds to cool and fragment, by the generations of stellar evolution needed to produce the heavier elements that make complex chemistry possible. The prediction is this: the very early universe, in the first few 100 million years, should contain only small, dim, nascent galaxies, primitive things, barely formed, the seeds of the magnificent spirals and ellipticals we see billions of years later, when Webb turned its mirror toward the deep field and began resolving objects at redshifts higher than any previously confirmed. The first season of data produced something that the modelers did not expect. In 2022 and 2023, preliminary photometric estimates suggested the presence of galaxies at redshifts above 10, 11, 12, galaxies that had formed within the first 400 million years of cosmic time, that appeared to be more massive, more luminous, and more chemically mature than lambda CDM predicted should be possible. Initial analyses suggested some of these objects might carry stellar masses 10 to 100 times larger than the models allowed for objects of their age. The headlines were immediate. "Webb breaks the universe," one popular science outlet announced. "Have galaxies been found that disprove the Big Bang?" asked another. Now, I want to be careful here, because the history of astrophysics is littered with premature announcements of paradigm shifts that turned out, under scrutiny, to be data artifacts, calibration errors, or resolved by a detail everyone had overlooked, and cosmologists, to their credit, were careful. The early Webb data was photometric, meaning it was based on the apparent colours of objects in the infrared, not on the definitive spectroscopic confirmation that actually tells you what you are looking at and how far away it truly is. Photometric redshifts can be wrong. They can be contaminated by foreground objects, by unusual dust properties, by AGN emission masking stellar light, so the community was cautious. But the caution had an uncomfortable quality to it, because even as the spectroscopic follow-ups came in, and some of the most extreme preliminary estimates were revised downward, others held. And then new, more distant objects were confirmed. And then JWST GSZ 14.0 was spectroscopically confirmed at a redshift of 1432, putting it 290 million years after the Big Bang, breaking the distance record for a confirmed galaxy by a margin that, in this field, is extraordinary. Its spectrum showed not just hydrogen emission, but oxygen, a heavy element that can only be produced inside stars over multiple generations of stellar evolution. A galaxy 290 million years old with measurable oxygen. That, if lambda CDM is fully correct, should not be there. And then, in May 2025, Webb broke its own record. A galaxy designated MOMSI 14, confirmed at a redshift of 14.44, was imaged during its formation a mere 280 million years after the Big Bang. The team that confirmed it, led by Rohan Naidu and including 45 co-discoverers, used a word in their paper title that I genuinely had to read twice to believe I was seeing in an astrophysics preprint. They called it a cosmic miracle, not a metaphor, not journalistic license. A cosmic miracle, because at 280 million years after the universe began, this galaxy is already compact, already luminous, already apparently forming stars at a ferocious rate and already so structurally coherent that it registers cleanly enough on the near-infrared camera of a space telescope to confirm its redshift to 2 decimal places. At a time when, according to the best models we have, the universe should still be in the process of assembling its first primitive stellar nurseries, something is already there, already bright, already in some sense already itself. This is the first crack in the architecture, not a clean fracture, not a definitive falsification, but a crack, a place where the model bends and where the bending requires explanation. And there are 2 others, 2 other threads running simultaneously through the Webb data, each one equally strange in its own domain, each one pressing on a different load-bearing wall of our understanding of the cosmos. One concerns what Webb found in the atmosphere of a world 124 light-years away. The other concerns an entirely new class of objects that before 2022 did not exist in any astrophysicist's taxonomy of the universe. We will get to both of them. But first, we need to understand why the early galaxy problem is not solved, even though several clever explanations have been proposed. Because this is the place where the science is genuinely, uncomfortably open. There is a standard playbook in astrophysics for when observations challenge established theory. Step 1. Check for errors in the observation. Step 2. Check for errors in the interpretation of the observation. Step 3. If the observation survives both checks, look for the most conservative modification to existing theory that can accommodate it. And only as a last resort, a distant, much resisted last resort, consider that the theory itself might require fundamental revision. The community ran this playbook with the early massive galaxy problem, and the result is, depending on how charitably you read the data, either reassuring or deeply unsettling, depending on which paper you happen to read first. The reassuring reading goes like this. Some of those early objects that appeared too massive turned out to have their luminosity substantially boosted not by enormous stellar populations, but by actively feeding black holes, AGN, active galactic nuclei, that outshine their host galaxies by factors of dozens or hundreds. If you are measuring stellar mass by total luminosity, and most of that luminosity comes from a black hole eating gas at a prodigious rate, you will dramatically overestimate how many stars are present. NASA published a paper in 2024 under the title "Webb finds early galaxies weren't too big for their britches after all," which, with characteristic understatement, suggested that the AGN contamination effect resolved much of the apparent excess. This is a legitimate and important point. Black holes in the early universe can masquerade as massive galaxies in photometric surveys, and the AGN fraction in early Webb objects does appear to be higher than in the nearby universe, which is itself interesting and worth understanding. But the reassuring reading does not resolve everything, because even after accounting for AGN contamination, some spectroscopically confirmed galaxies at very high redshifts show chemical signatures, oxygen, neon, carbon, that require stellar populations substantially older or more productive than lambda CDM straightforwardly predicts. JWST Z14, with its confirmed oxygen, is the clearest example. You cannot fake oxygen emission with an AGN. Oxygen is heavy. It was forged in stellar cores over tens or hundreds of millions of years of nuclear burning, and then distributed into the interstellar medium by supernova explosions. To have measurable oxygen at a redshift of 14.32 means that star formation began earlier, proceeded faster, or was more efficient than the standard model allows for. Several proposals have been put forward. One involves a non-universal stellar initial mass function, a suggestion that in the early, dense, hot universe, the first stars were systematically more massive than the stars being born today, which would accelerate both stellar evolution and heavy element production. Another involves modifications to the efficiency of star formation itself, the fraction of available gas that converts to stars per unit time, suggesting that early galaxies were unusually productive. A third, and more radical, avenue involves modifications to the dark matter model, suggestions that perhaps dark matter is not entirely cold and collisionless, but has properties that allow halos to assemble more rapidly in the early universe. None of these proposals, I want to be precise, has been confirmed. None is the consensus explanation. The field is genuinely open, and then there is a separate thread, one I find genuinely destabilizing in its implications, that runs not through galaxy formation but through the fabric of the universe itself. The Hubble tension. The Hubble constant is the rate at which the universe is currently expanding. Measure it using the cosmic microwave background, essentially extrapolating forward from the primordial universe using lambda CDM, and you get a value of approximately 67.4 kilometers per second per megaparsec. That means a galaxy 1 megaparsec away, roughly 3.26 million light-years, is receding at 67.4 kilometers per second due to the expansion of space alone. This number is derived from the physics of the early universe, and it is extremely precise. Now measure it directly, using the cosmic distance ladder, calibrating distances using Cepheid variable stars, then supernovae, then the galaxies containing them, building up a chain of standard candles that lets you measure recession velocities independently of any cosmological model. Before Webb, this method consistently produced a higher number, approximately 73 kilometers per second per megaparsec. The gap between 67.4 and 73 is the Hubble tension, and for years it refused to go away. It sat at a statistical significance of approximately 5 sigma, the threshold above which, in physics, we conventionally begin calling things discoveries, which is deeply uncomfortable because a 5 sigma tension in your two most independent measurements of the same fundamental constant means either one measurement is wrong or your model is missing something real. Webb was supposed to help resolve this by extending Cepheid measurements further and by independently calibrating distances using different standard candles, specifically tip of the red giant branch stars. Webb had the power to identify whether the tension was a measurement error or a genuine physical signal. In 2025, the results came in. A team led by Wendy Friedman at the University of Chicago, incorporating the largest Webb dataset yet assembled for this purpose, produced a Hubble constant measurement of 70.4 kilometers per second per megaparsec, with an uncertainty of 3%. That number sits between the two previously discrepant values. It overlaps within its error bars with both the CMB-derived value and the Cepheid-derived value. The tension in Friedman's analysis appeared to dissolve, not because the previous measurements were wildly wrong, but because the Webb data, with its superior resolution and reduced systematic uncertainties, appears to shift the distance ladder calibration in a direction that reduces the discrepancy. But, and this is a genuine and important but, not everyone agrees. Other analyses using Webb data, incorporating different standard candles, different calibration assumptions, different subsets of the data, find that the tension persists. Some find a higher value, some lower. The community is not converged, and simultaneously, completely independent evidence from a different instrument, the Dark Energy Spectroscopic Instrument, DESI, surveying the large-scale structure of the universe using baryon acoustic oscillations, has produced evidence that dark energy itself may not be constant, that lambda, the cosmological constant, may not be constant at all, that the force driving the accelerating expansion of the universe might be weakening over cosmic time. If that is true, if dark energy is not a fixed constant but an evolving quantity, then the implications are staggering. The entire framework of lambda CDM rests on the assumption that the cosmological constant is, well, constant. The lambda in the name is precisely that assumption, and the Quantum magazine headline in March 2025 summarized the situation with admirable directness. Is dark energy getting weaker? New evidence strengthens the case. I will be honest, I find this particular thread of the story the one that keeps me thinking longest. Because the galaxy formation problem, the too big too soon problem, might be resolved by astrophysics, by a better understanding of how stars form, or how black holes grow, or how dark matter halos assemble. Those are hard problems, but they are internal to the existing model. But if dark energy is evolving, that is not an astrophysics problem. That is a cosmology problem. That is a problem that sits at the foundation of everything we think we know about the shape and fate of the universe. 3 unanswered questions are running simultaneously now, and I want you to hold all 3. Why are the earliest galaxies already so mature? Is the Hubble constant genuinely resolved, or is the tension still there, hiding in the systematic uncertainties? And is the force that is pulling the universe apart weakening? And if it is, what does that mean for everything? We will return to all 3, but before we can fully appreciate what Webb has found, we need to meet the strangest objects in its catalogue. The objects that forced astronomers to coin a new category and then to coin a new name for what that category might actually contain, the little red dots, and what they might be. In the first deep field images returned by James Webb in late 2022, something caught the attention of several research groups simultaneously. Scattered across the infrared field, tiny, compact, intensely red points of light appearing in the epoch of the universe between 600 million and 1.5 billion years after the Big Bang, were objects that defied immediate classification. They were too compact to be typical galaxies. Their spectral signatures were deeply unusual, broad emission lines suggesting violent, high-velocity gas motion, combined with a steeply red continuum unlike any galaxy population previously catalogued. Their luminosities, if interpreted as coming from stellar populations, implied stellar masses that the models said were impossible at their ages. And yet they were there, in their dozens, and then their hundreds, appearing consistently across multiple deep fields and observing programs as if the early universe had been seeding itself with a type of object that nobody had written a theoretical paper about because nobody had imagined it needed to exist. They were called the little red dots. This name has the charming quality of all astronomical colloquialisms. It describes exactly what they look like and nothing whatsoever about what they are. The proposals came quickly. Some researchers suggested they were compact star-forming galaxies caught in an extreme burst of star formation, with dust reddening their optical emission and boosting the infrared. Others argued they were dominated by active galactic nuclei, rapidly accreting black holes, which would explain the broad emission lines and the extreme luminosities without requiring implausibly large stellar masses. A third proposal, considerably more exotic, suggested they might represent an entirely new class of massive stars, the theorized population 3 stars, the hypothetical first-generation stellar objects, composed of nothing but primordial hydrogen and helium, formed before the universe had produced a single atom of heavier elements. Each proposal had problems. The AGN interpretation did not fully explain the specific combination of spectral features. The compact starburst model required implausibly efficient star formation, and population 3 stars were expected to produce very different spectroscopic signatures from what was being observed. Then, in the months running through 2025, a team of astronomers working with Webb's NIRSpec spectrograph obtained something that had previously been out of reach: the deepest, most detailed spectrum ever taken of a single little red dot. The target was an object designated Glimpsen 775. It sits at a cosmological redshift of 3.5, meaning the light we observe from it left its source approximately 8 billion years after the Big Bang. Not as early as the most extreme little red dots, but still in the period of intense cosmic evolution before the universe settled into the relatively stable architecture it has today. And it had a critical advantage. It was situated behind the galaxy cluster Abell S63, which acts as a gravitational lens, using the warped space-time around its mass to magnify and brighten objects behind it. Combined with 30 hours of Webb observation time, the lensing effect made the total equivalent observing depth approximately 80 hours. The result was a spectrum containing more than 40 individual spectral lines, more detail than any previous little red dot spectrum by a considerable margin. Led by Vasily Kokorev at the University of Texas at Austin, the team began identifying what those 40-plus lines were telling them. And the picture that assembled itself, piece by piece like a mosaic with a subject nobody had painted before, was this: Glimpse 7775 is not a compact galaxy. It is not a starburst. It is not a conventional AGN. It is a supermassive black hole, rapidly accreting, meaning consuming surrounding material at a ferocious rate, enveloped in a dense, layered cocoon of partially ionized gas so thick that it absorbs the X-rays the black hole would otherwise emit and reprocesses the energy, re-radiating it in the specific infrared and optical wavelengths that make these objects appear as small, intensely red points in Webb's field of view. The model has a name, BH star, black hole star. Not a black hole and not a star, but a new category of cosmic object. A gravitational monster wrapped in a gas shroud so dense it glows, behaves, and emits like nothing in the standard astronomical catalogue. The evidence for this model in Glimpse 17775 spectrum is, to use the scientific term that applies here, remarkable. 16 ion emission lines forming what the team described as an ion forest, a density of ion emission that requires a powerful high-energy source, consistent with a black hole accretion disk, to produce hydrogen and helium line profiles that cannot be fitted by a simple rotating gas cloud model, but are perfectly described by the broadening effects of electron scattering through a dense, layered medium, exactly what you would expect from a thick gas cocoon. Oxygen line ratios that require hard radiation from a compact, energetic source. Helium absorption and fluorescence signatures that, individually and independently, point to a dense medium enveloping something extremely powerful at the centre. Kokorev described the process of reading the spectrum as picking up puzzle pieces from the floor. Some looked like nothing at first. Then a few combined. Then the picture emerged. And the picture, the black hole star model, also resolves one of the most persistent puzzles about little red dots, why they are so faint in X-rays. A rapidly accreting supermassive black hole should be a luminous X-ray source. Active galactic nuclei in the nearby universe shine brilliantly in X-rays, but little red dots in Webb observations stacked with Chandra X-ray observatory data appear X-ray quiet. The BH star model explains this directly. The dense gas cocoon absorbs the X-rays. They are produced at the centre and never escape. The cocoon reprocesses the energy into the infrared and optical emission that we actually detect. The team was careful to note that Glimpse 17775 has one unusual feature compared to typical little red dots: a giant host galaxy surrounding it, producing excess blue light that competes with the characteristic red continuum. But this is not inconsistent with the BH star model. The black hole star sits at the centre. The host galaxy wraps around it. Together they produce an object that looks, from 1.8 billion light-years away, like a fuzzy red smear with a yellow core. Here is what I find genuinely arresting about this. We have observed black holes for decades. We have observed accretion disks. We have observed AGN, quasars, blazars, Seyfert galaxies, radio galaxies, an entire taxonomy of objects powered by gravitational engines at their centres. And yet in the 30-year history of infrared astronomy, across thousands of deep-field observations with Hubble and Spitzer, and every ground-based instrument we could point at the sky, nobody found a little red dot. They exist, apparently in abundance, in the early universe, and they are completely absent from the catalogues of the nearby universe, which means either we have never had the capability to see them at the distances where they appear, which is true. Webb is the first telescope sensitive enough to detect them, or they existed in the early universe and then transitioned into something else. Some other class of objects that does exist in our catalogues, the most compelling hypothesis, and the one that is gaining traction in the community, is that the little red dots, the BH stars, are the progenitors of the supermassive black holes that sit at the centres of almost every large galaxy in the nearby universe, including our own Milky Way. The galaxy at the centre of the Virgo cluster, M87, has a black hole of 6.5 billion solar masses. Our own Milky Way's central black hole, Sagittarius A, has a mass of 4 million solar masses. Where did these black holes come from? How did they grow so large so quickly when we observed the universe becoming old enough to contain them? The BH star model offers an answer. They began as violently accreting objects wrapped in gas cocoons in the early universe. growing at rates that defy what we previously thought possible. Hidden from detection by the very cocoons that fed them, the little red dots, if this model is right, are not a curiosity. They are not a footnote. They are the birth certificates of the gravitational engines that structured the entire subsequent history of the universe. But, and there is always a but in this story, the model is not confirmed. Kokorev himself noted that other exotic theories are being proposed, and that in a year or two, the field may have a final answer, or it may have a better question, one thread resolved, provisionally. Two others still open: the galaxy formation problem, the dark energy evolution question, and a third thread, the strangest of all, that has nothing to do with distant galaxies, and everything to do with a world that is, on cosmic scales, practically next door. His name is Niku Madhusudan. He is a professor of astrophysics and exoplanetary science at the University of Cambridge's Institute of Astronomy. He is, by all accounts, the kind of scientist who has spent so long inside a single problem that he can no longer separate the intellectual from the personal. The kind of researcher for whom a particular planet is not a data point, but a preoccupation, something he returns to the way a novelist returns to a character who will not behave as expected. Madhusudan's preoccupation has a name: K2-18b. The planet was discovered in 2015 by the Kepler Space Telescope in an unremarkable detection buried in a catalogue of hundreds of transit signals. It orbits a red dwarf star, a small, cool, faint star of the spectral class M3V, roughly half the radius of the Sun and considerably less luminous, in the constellation Leo, 124 light-years from Earth. Its orbital period is 32.94 days. Its radius is approximately 2.61 times Earth's. Its mass is approximately 8.63 times Earth's. These numbers put it in a category called sub-Neptune, or sometimes super-Earth, a class of planets that is the most abundant in the galaxy, as far as we can determine, and yet has no analogue in our own solar system. For several years, K2-18b was one of many planets in an expanding catalogue, notable primarily for orbiting within its star's habitable zone. The range of orbital distances where liquid water might theoretically persist on a planetary surface, but not especially distinguished. Then in 2019, water vapour was detected in its atmosphere. This was significant. It was the first detection of water vapour in the atmosphere of an exoplanet that was not a hot Jupiter, not one of those close-orbiting gas giants whose extreme temperatures and enormous sizes make atmospheric characterization relatively straightforward. A water vapour detection in a habitable zone sub-Neptune was a different kind of result. It meant the planet was worth watching, and Madhusudan watched it. More than that, he theorized it. In 2021, he and his colleagues at Cambridge published a paper that introduced a new category of planetary architecture, the Haitian world, from hydrogen and ocean. A Haitian world is a sub-Neptune with a deep hydrogen-rich atmosphere overlying a global liquid water ocean, warmed from below by internal heat and insulated from above by the greenhouse effect of the hydrogen envelope. Madhusudan argued that Haitian worlds might be the most common habitable environments in the galaxy, far more widespread than rocky Earth-like planets in tight orbits around Sun-like stars. And he argued that K2-18b might be exactly this: a world covered entirely by a warm, shallow sea beneath a sky the colour of nothing in Earth's experience. But the key question was not whether K2-18b had an ocean. The key question, the one that Madhusudan could not let go of, was whether anything lived in it. To answer that, you need biosignatures, chemical signals in a planet's atmosphere that indicate the presence of biological processes, because life, if it exists, should produce gases as metabolic byproducts that would otherwise not be there, or would not persist in the concentrations observed, or would not appear together in the specific ratios that only biology consistently produces. On Earth, the biosignature combination that most clearly marks our planet as inhabited is the coexistence of oxygen and methane, two gases that react with each other and would not both be present simultaneously in large quantities without something continuously replenishing them. That something is life. But for a hydrogen-rich Haitian atmosphere, oxygen is not the right biosignature. The chemistry is different, and Husadan and his collaborators worked through the theoretical possibilities and identified a candidate, dimethyl sulfide, or DMS. On Earth, DMS is produced primarily by marine phytoplankton, single-celled oceanic organisms that synthesize it as part of their sulfur metabolism and release it into the ocean, where it evaporates into the atmosphere. It is the chemical responsible for the distinctive smell of the sea. And on Earth, it is produced in quantities so small, generally below 1 part per billion by volume in the atmosphere, that it would be extraordinarily difficult to detect remotely. But on a Haitian world, the theoretical models predicted that DMS could build up to concentrations thousands of times higher. If K218b had an ocean, and if that ocean teemed with organisms analogous to Earth's phytoplankton, the DMS in its atmosphere might reach concentrations detectable by an instrument precise enough to resolve individual molecular absorption features from 124 light-years away. James Webb Space Telescope is that instrument. When Webb turned its attention to K218b in 2023, the first results were already extraordinary. Carbon dioxide and methane were both confirmed. The first simultaneous detection of both gases in the atmosphere of a habitable zone sub-Neptune. This was consistent with the Haitian model. It was not proof of life, but it was the right atmospheric chemistry for the right kind of world. And then came the 2025 results, published in the Astrophysical Journal Letters by Madhusudan and his team, including co-authors Mons Holmberg from the Space Telescope Science Institute and Subhajit Sarkar of Cardiff University. The paper reported the detection of spectral features consistent with DMS and its chemical sibling, dimethyl disulfide, or DMDS. Both molecules come from the same chemical family. Both are predicted to be biosignatures, and the concentrations implied by the spectroscopic data were not trace quantities. They were estimated at over 10 parts per million, more than 10,000 times the concentration of DMS in Earth's atmosphere. When Holmberg saw the results hold through multiple independent analyses and robustness tests, he described it as incredible. That is the word he used, not in a press release. In a quoted scientific statement, incredible realization, the team was carefully, meticulously, almost painfully careful. Madhusudan stressed that the detection must be scrutinized, that more data is required before any claim of discovery is appropriate. Previously unknown abiotic, non-biological, chemical processes on Haitian worlds might produce DMS or DMDS in the observed quantities without any organism being involved. He called for more theoretical work and experimental tests. He said explicitly that it's vital to be deeply skeptical of their own results, but he also said something else. Something that, when I read it, I found I needed to put down and sit with for a moment. Decades from now, we may look back at this point in time and recognize it was when the living universe came within reach. The living universe. He did not say a planet that might have life. He said the living universe. A universe in which life is not an accident of one planet around one star in one galaxy, but a property, a feature, a recurring phenomenon distributed across cosmic time and space. Now, the NASA-led study that re-examined the K218b data produced a more cautious assessment, finding the evidence for DMS inconclusive and emphasizing the substantial systematic uncertainties in molecular detections of this kind. The absorption features of DMS and DMDS overlap with one another and potentially with other molecules in the wavelength range probed by Webb's MIRI instrument. Disentangling them requires assumptions about the atmospheric structure, the temperature profile, the presence or absence of cloud layers. These assumptions carry uncertainties. Multiple independent research groups, analysing the same data with different models, have not yet converged on a single answer. This is science working correctly. The disagreement is not a failure. It is the mechanism by which extraordinary claims are tested against extraordinary evidence. And the evidence, as of mid-2025, is the strongest yet for a biosignature molecule in the atmosphere of a habitable zone exoplanet. Not confirmed, not definitive, but the strongest yet. Here is what I think about Niku Madhusudan that has nothing to do with spectral modelling or Bayesian analysis. He proposed the category of planet, the Haitian world, that made K218b worth looking at for biosignatures. He identified the biosignature, DMS, that was theoretically detectable on such a world. He designed and led the observational campaign that detected the candidate signal. And he has spent years building the theoretical framework within which the result can even be interpreted. This is what scientific vision looks like. Not a sudden discovery, but a decade-long wager on a specific idea about what the universe might contain, prosecuted with patience and precision until the instruments catch up to the hypothesis. And his hypothesis is still alive. Contested, uncertain, awaiting more data. But alive, 3 questions open. One is whether the early universe contains something fundamentally inconsistent with lambda CDM. One is whether dark energy is evolving. And one is whether, 124 light-years away, an ocean on an alien world is producing a gas that we have only ever seen life produce before. The stakes could not be higher on any of the 3. But the stakes of the third, the single most intimate, the one that touches the question every human culture has ever asked, are of a different order entirely, because cosmological models can be revised. The Hubble constant can be remeasured. But if there is life on K218b, then the Copernican revolution, the long, slow dethronement of humanity from the centre of the cosmos, which began with Galileo and has been accelerating ever since, reaches its logical terminus. We are not special, we are not alone. And everything we have ever told ourselves about the uniqueness of our existence, the singular improbability of our being here, becomes a story we told when we didn't know any better. That is not a scientific statement, it is a human one, and Madhusudan made it, and it deserves to be heard. Let us now do something that science documentaries rarely do explicitly. Let us pull back to the widest possible view and ask what all of this means together. 3 threads, a distant galaxy that should not be mature enough to contain oxygen, a class of objects that represent an entirely new category of cosmic entity, potentially the progenitors of every supermassive black hole in the observable universe, and a chemical signal in the atmosphere of an alien world that, if biological, would be the most consequential discovery in the history of human science. What, if anything, connects them? The answer might be the question we have not yet fully asked. Not what individual discoveries mean, but what they say together about the architecture of our ignorance. Because Webb is not revealing a universe that is stranger than we expected in isolated places. It is revealing a universe that is stranger than we expected at every scale simultaneously, from the 280 million year epoch of MOMSI 14 to the 1.8 billion year epoch of Glimpse 17775 and the little red dots, to a world 124 light-years away that might be alive. These 3 timescales are separated by billions of years. These 3 distance scales span from cosmic to nearly local, and yet all 3 are producing data that does not fit cleanly in our existing theoretical boxes. That could be coincidence. Individual anomalies, each with its own resolution, none connected to the others by anything deeper than the fact that Webb is powerful enough to find things previous instruments missed. Or it could be something more systematic, a sign that our models of both cosmological structure and planetary habitability have been built on assumptions that seemed reasonable when we had limited data, and that now, with better data, are beginning to show their seams. I want to talk about what the stakes look like if several of these threads are real. Not all of them necessarily, not simultaneously, but let us consider what the scientific landscape looks like if, say, 2 of the 3 solidify into genuine results over the next decade. Start with the early universe problem. If spectroscopic surveys over the next 5 years confirm that galaxies at redshifts above 10 are systematically more massive, more chemically evolved, and more structurally mature than lambda CDM predicts, the response cannot be limited to tinkering with astrophysical parameters. If the discrepancy is large enough, it points to something wrong in the cosmological framework that governs how structure grows. The most natural candidates are modifications to dark matter, cold dark matter the CDM in lambda CDM, is cold in the specific technical sense that it was moving slowly at the time of matter radiation equality, allowing structures to form from the bottom up. Small halos first, then larger ones assembling hierarchically over time. This bottom-up, hierarchical assembly is a core prediction of the cold dark matter model, that if the early universe is producing very large structures very quickly, one natural explanation is that dark matter is not entirely cold, that it has a component with different properties, warmer or more self-interacting, that allows halos to assemble faster. Modifications to the dark matter model, even modest ones, would ripple through every simulation, every prediction, every theoretical framework we use to understand galaxy formation and large-scale structure. Now add the dark energy thread. The DESI results, suggesting that the cosmological constant may not be constant, are based on the most comprehensive survey of baryon acoustic oscillations ever conducted. The subtle imprints of sound waves from the early universe, fossilized in the large-scale distribution of galaxies, serve as a standard ruler for measuring cosmic distances across billions of light years. The DESI collaboration measured baryon acoustic oscillations across a billion galaxy sample and found hints, not proof, but hints with statistical significance that grows with each data release, that the equation of state of dark energy has evolved over cosmic time. If dark energy weakened in the past and is weakening now, the universe will not end in the heat death that cold dark matter plus a stable cosmological constant predicts, an infinitely dark, infinitely diffuse, infinitely cold expansion to nothing. It might end differently, or it might oscillate, or the weakening might reverse. We genuinely do not know, and the implications for the distant future of cosmic structure, for whether the gravitationally bound structures that currently exist will survive or dissolve, are not trivial. Now add the biosignature thread. If K218b's DMS signal is confirmed, not by one team but by multiple independent analyses using different modelling approaches and ideally by additional observations with Webb or future telescopes, it does not merely confirm life on one world. It statistically transforms our understanding of life's prevalence in the universe. K218b is not a special star. K218 is an M-dwarf, the most common class of star in the galaxy. Approximately 75% of all stars in the Milky Way are M-dwarfs. Up to 80% of M-dwarfs are estimated to have planets in their habitable zones. If a Haitian sub-Neptune around a run-of-the-mill M-dwarf can develop a biosphere, then the galaxy is not just habitable, it is inhabited. Richly, widely, perhaps overwhelmingly inhabited. Not by intelligent beings necessarily. K218b, if it is alive, probably carries nothing more complex than ocean microbes, but by life, by metabolism, by chemistry that is more than chemistry. This is what the Drake equation has been trying to quantify since 1961. The number of civilizations in the galaxy capable of communication. But the more fundamental question, the one that precedes the Drake equation, is the one Frank Drake himself was trying to ask. What fraction of suitable environments actually develop life? If K218b is alive, the answer to that question shifts from we have no data to at least 1 out of 1 observable case, which is, in Bayesian terms, a dramatically different prior for every subsequent calculation about the prevalence of life in the universe. Here is where all three threads converge, and where I think the deepest implication lives. James Webb was designed to answer specific questions. Questions about the first light of the universe, about the formation of galaxies, about the atmospheres of exoplanets, and it is answering them. But it is answering them in a way that produces new, harder, more fundamental questions faster than the old ones are resolved. Every confirmed early galaxy pushes the horizon of our ignorance further back in cosmic time. Every little red dot that turns out to be a black hole star raises new questions about the birth of the gravitational engines that assembled the universe we live in, and every new observation of K218b either strengthens or tests a signal that, if real, would restructure our understanding of where in the universe to look for life and why. Science does not always proceed by elegant theory followed by neat confirmation. Sometimes it proceeds by discovery, followed by bewilderment, followed by, slowly, a new framework that is larger and stranger than the one it replaced. The Copernican revolution was not complete in Copernicus's lifetime. The quantum revolution was not understood in Planck's lifetime. The revolution that James Webb may be initiating, if these threads are real, would not be complete in Madhusudan's lifetime, or Kokorev's or Naidu's. It would be the work of generations. But it begins here, in the data streaming from a golden mirror orbiting 1.5 million kilometers from Earth, in the spectra of objects no human instrument has ever seen before, in the signal of a molecule produced by ocean life on a world that circles a dim red star in the constellation Leo. The stakes are not merely scientific, they are existential in the most literal sense of that word. They concern the nature of existence itself, how matter organizes, how time began, whether the cosmos in its unimaginable scale and age has found a way to know itself through the medium of life. Those are not small questions, and Webb is, for the first time in human history, placing them within the range of empirical science. At this point, I want to do something that is not always done in popular science communication. I want to downshift, not because the story is less extraordinary than it appears. It genuinely is extraordinary, but because extraordinary claims require extraordinary precision, and precision requires acknowledging what the data actually says versus what the data allows us to infer, versus what the data definitely does not yet support. Let us take each thread in turn. On the early galaxy problem and the question of whether lambda CDM is under genuine threat, the consensus position among cosmologists, as of mid-2025, is nuanced. The initial alarm, the Webb breaks cosmology headlines of 2022, has been substantially tempered by more careful spectroscopic analysis. The NASA paper noting that AGN contamination explains much of the apparent excess in early galaxy masses is a real and important result. A non-trivial fraction of the objects that appeared to be extraordinarily massive were partly or largely powered by accreting black holes, not stellar populations, and once that contribution is subtracted, the residual stellar masses are more consistent with existing models. However, and this however is load-bearing, more consistent does not mean fully consistent. The community of researchers working on high redshift galaxies is not uniformly reassured. Papers published through 2024 and 2025 continue to report individual objects, like JWST GSZ140 and MOM-Z14, carry spectroscopic features, oxygen, neon, ionized carbon, that are genuinely difficult to explain within the standard hierarchical assembly picture, without invoking unusually high star formation efficiencies, or top-heavy stellar initial mass functions, or some modification to the dark matter model. The community is debating which of these modifications is most parsimonious, most consistent with other constraints, and most testable with future observations. The honest position is this: lambda CDM is not broken, but it is stressed. The data from the first 3 years of Webb operations has identified persistent, quantitative tension between the observed properties of high redshift galaxies and the most straightforward predictions of the standard model, and the resolution of that tension is not yet in hand. On the Hubble tension, the Friedman 2025 result, measuring a Hubble constant of 70.4 kilometers sec-naught pp with a 3% uncertainty, is genuinely significant. If confirmed and if its systematic uncertainties are correctly characterized, it suggests that the discrepancy between CMB-based and distance ladder-based measurements may be partly, or perhaps largely, attributable to calibration errors in the previous Cepheid-based distance scale, specifically in the period luminosity relations used to calibrate Type Ia supernovae. The proximity of the new Webb-based measurement to the CMB-derived value of approximately 6768 is striking, and has led several commentators to suggest the tension may be resolving. But there are 2 important caveats. First, the Friedman result is not the only Webb-based Hubble constant measurement, and other analyses using Webb data, with different calibrators and different methodology, produce different answers that are not inconsistent with the previous Cepheid-based higher value. the community has not converged. Second, the DESI baryon acoustic oscillation results are independent of the distance ladder entirely, and they suggest that something unusual may be happening with dark energy, which could independently explain why the CMB extrapolated and local distance ladder measurements have disagreed. If dark energy is evolving, then the simple extrapolation from the CMB to the present day using a fixed cosmological constant is not correct, and the apparent tension may be a symptom of that more fundamental mismodelling rather than a calibration error. These two explanations are not mutually exclusive. The tension might be partly a calibration issue and partly a cosmological model issue. Unravelling the two contributions is the work of the next decade, and it requires both more Webb observations and more DESI data, and, eventually, next-generation instruments like the Vera Rubin Observatory's Legacy Survey of Space and Time and the Nancy Grace Roman Space Telescope. On the little red dots and the BH star model, the situation is more developed than it was even 12 months ago, but it is still evolving rapidly. The Glimpse 17775 paper by Kokorev et al. Represents the most compelling observational case for the BH star interpretation, and the community reception has been broadly positive. The more than 40-line spectrum, the iron forest, the electron scattering broadening of the emission lines, the helium fluorescence and absorption. These are independent lines of evidence that are difficult to explain without the dense gas cocoon model, but significant questions remain. One is the origin of the black hole itself. If a little red dot is a rapidly accreting supermassive black hole at redshift 3.5, the black hole must have assembled a very large mass, potentially hundreds of millions to billions of solar masses, in a very short time. The Eddington limit sets a theoretical maximum on how fast a black hole can grow by accretion, because the radiation pressure from infalling material eventually pushes back against more material falling in. Growing a black hole of 100 million solar masses within the first billion years of the universe requires either super Eddington accretion, feeding faster than the classical limit allows, or a very massive seed black hole to start with, or both. The BH star model does not fully explain either the seed mass or the accretion history. It describes what these objects appear to be, not how they got there. A second open question is the connection to the earliest galaxies, to MOM Z14 and JADA's GSC 14-0. If little red dots are the precursors to supermassive black holes, and if supermassive black holes exist at the centres of very early, very massive galaxies, then there should be a connection between the BH star phase and the formation of the massive galaxies that appear too early in Webb's deep fields. Some researchers have proposed that the BH star phase comes first, that a black hole surrounded by a dense gas cocoon drives rapid star formation in the surrounding material, seeding the galaxy that then assembles around it. Others argue the order is reversed or simultaneous. The data are not yet sufficient to determine the sequence. On K2-18b, I want to be particularly careful here because this is the thread where the stakes are highest and the risk of overinterpretation is greatest. The detection of DMS and DMDS candidate features in K2-18b's Myri spectrum is real. The team ran multiple independent analyses and robustness tests, and the signal survived them. But several critical uncertainties remain. First, the spectral resolution of Myri at the relevant wavelengths is such that DMS and DMDS cannot be cleanly separated from each other, and potentially not from all other molecules that absorb in the same wavelength range. More observations, ideally using Webb's other instruments at different wavelengths, or future space telescopes with higher resolution, are needed to confirm the molecular identification. Second, the concentrations implied, greater than 10 parts per million, are consistent with a biological source, but are not proof of one. Multiple papers published in 2024 and 2025 have explored abiotic pathways, non-biological chemical reactions, that might produce DMS or DMDS in hydrogen-rich planetary atmospheres. Some of these pathways are plausible under the right conditions. Whether they can produce the observed concentrations under the specific conditions of K2-18b's atmosphere is not yet established. either observationally or experimentally. Third, a NASA-led reanalysis of the K2-18b data produced a more cautious interpretation, finding the evidence inconclusive, a word that falls considerably short of detection in the vocabulary of observational astronomy. The appropriate characterization, therefore, is the James Webb Space Telescope has detected the strongest observational hint yet for a biosignature molecule in the atmosphere of a habitable zone exoplanet. It is a hint, a signal that warrants urgent, serious, methodologically rigorous follow-up. It is not a confirmed detection of life. It is not a result that in its present form would withstand the standard of evidence that the scientific community applies to claims of this magnitude. But neither is it nothing. And the reason it is not nothing, the reason it commands the attention and resources that it does, is that it falls exactly where the hypothesis predicted it would fall. And Husadan's 2021 theoretical work predicted that Haitian worlds should accumulate detectable concentrations of DMS if life is present. Webb is now observing exactly the kind of spectral feature in exactly the kind of world that the theory said to look at. Predictions confirmed by observation are the currency of science, and this prediction, even if the confirmation is not yet definitive, is confirmed enough to make the next observations urgent. There is one more layer of nuance that I think deserves explicit acknowledgement, and that is the question of what NASA cannot fully explain actually means in the context of this script's title, which I chose not because it is inaccurate, but because it is precisely accurate in a way that requires unpacking. NASA, or more precisely, the community of scientists who operate and interpret Webb's data, is not simply baffled by these results. They have models, they have candidate explanations, they have active, productive debates between competing interpretations. What they do not have is consensus. What they do not have is proof. What they do not have is closure. That is not a failure of science. That is science at the frontier. The most productive, consequential, intellectually electric region of scientific inquiry is not the settled territory where the textbooks are written. It is the contested border zone where multiple models compete, where each new data point shifts the weight of evidence toward one interpretation or another, where careers are built on being right before everyone else catches up, and where the possibility of being memorably, productively wrong is always present. This is where Webb is operating. And this is why, 3 years into its science mission, it has produced more questions than answers. That is precisely what a transformational instrument is supposed to do. What would count as resolution? For the early galaxy problem, it would be a comprehensive spectroscopic survey of hundreds of confirmed high redshift galaxies, with stellar masses and star formation histories robustly separated from AGN contributions, producing a statistical distribution that either does or does not fit lambda CDM with its current parameters. For the dark energy question, it would be a Hubble constant measurement with uncertainties below 1% from multiple independent methods converging on the same value, combined with additional DESI data releases that either confirm or refute the dark energy evolution signal. For the little red dots, it would be additional deep spectra of additional objects, not one, but a population, establishing the BH star model as the universal interpretation rather than the correct one for Glimpse 7775 specifically. And for K2-18b, it would be additional Webb observations at different wavelengths, plus the commissioning of future telescopes like the Habitable Worlds Observatory, the planned NASA flagship mission explicitly designed to search for biosignatures on Earth-like exoplanets, with sensitivity far exceeding Webb's current capabilities. All of this is planned. All of this is in the pipeline. The next decade of astronomy is going to be the most data-rich in the history of the field. And the James Webb Space Telescope, still in its primary mission phase, still accumulating observing time and science products and surprises, is the leading instrument of that decade. The questions are open. The methods for answering them exist, and the people answering them are among the most capable scientists our civilization has ever produced. That is not a guarantee of revelation. but it is the best possible preparation for it. The James Webb Space Telescope is designed to operate for at least 20 years. The fuel budget, the propellant used for station keeping at the L2 point, was optimized so efficiently during the Ariane 5 launch in December 2021 that the mission designers now estimate Webb could remain fully operational through the early 2040s. 20 years is a long time in astrophysics. 20 years ago, in 2006, we had not yet confirmed the first exoplanet atmosphere with Spitzer. We did not yet know the mass of Sagittarius A with the precision we now have. We had not yet mapped the cosmic web at the resolution provided by current galaxy surveys. 20 years in this field is, empirically, enough time for the landscape to change beyond recognition. What does Webb's next phase look like? And what instruments and missions are being built or planned to follow where Webb's questions are leading? On the early galaxy front, the next critical step is a systematic, statistically robust spectroscopic survey of galaxies at redshifts above 10, designed specifically to measure stellar masses without AGN contamination and to quantify the frequency of heavy elements in these extreme environments. Webb's ANEA spec instrument, the near-infrared spectrograph that produced GLIMPSE 7775's extraordinary 40-line spectrum, is capable of observing up to 200 objects simultaneously through its microshutter assembly, a silicon wafer containing 248,848 individually controllable shutters, each the width of a human hair. With this capability, Webb can build statistical samples of high redshift galaxies far more rapidly than the individual pointed observations that have characterized the first years of science operations. Several such surveys are already planned, and the data they return over the next 5 years will determine whether the early galaxy problem deepens or resolves. In parallel, the Nancy Grace Roman Space Telescope, due to launch in late 2026, will conduct wide-field infrared surveys covering thousands of square degrees of sky, identifying hundreds of thousands of high redshift galaxy candidates for follow-up with Webb. Roman's combination of wide-field, roughly 100 times larger than Webb's field of view, and infrared sensitivity will enable a census of the early universe at a scale that individual deep-field programs cannot achieve. The synergy between Webb and Roman, one going deep, one going wide, is designed precisely to produce the kind of statistically complete samples that can test cosmological models rather than merely constrain them. On the Hubble tension, the resolution pathway is similarly structured. Additional Webb observations of distance calibrators, Cepheid variables, tip of the red giant branch stars, surface brightness fluctuations, gravitational lensing time delays, from multiple independent teams using multiple methods, will either converge on a consistent value or continue to diverge, and either outcome is scientifically valuable. The Vera Rubin Observatory's legacy survey of space and time, commencing full science operations from its site in Chile, will produce a dataset containing billions of individual stellar measurements over 10 years, enabling distance calibrations of unprecedented precision and uniformity. And DESI's continued baryon acoustic oscillation survey, expected to complete its 5-year program with a galaxy sample exceeding 40 million objects, will provide the most precise measurement yet of cosmic structure and its evolution with time, directly testing whether dark energy is evolving and by how much. If dark energy is genuinely evolving, the theoretical implications are being worked out now. The simplest models of evolving dark energy treat it as a scalar field, a physical field with a potential energy that changes slowly over cosmic time, a concept sometimes called quintessence. Quintessence models can accommodate a slowly weakening dark energy without violating any known physical principle, but they do introduce a new degree of freedom, a new fundamental field, into the standard model of particle physics, and that new field has observable consequences beyond its effect on cosmic expansion. It should produce small but detectable variations in the coupling constants of fundamental forces across cosmic time. Future spectroscopic surveys of quasar absorption lines, measuring the fine structure constant and other fundamental parameters in the spectra of distant gas clouds will probe whether those variations exist. If they do, they would confirm not just that dark energy is evolving, but that the fabric of physics itself is not as static as we have always assumed. I want to pause on that. The fabric of physics itself, the possibility that the constants we use to describe all of nature, the speed of light, the electron charge, the gravitational constant, might vary across cosmic time and space is not new. It has been proposed and tested for decades, and so far the data are consistent with constancy. But consistent with constancy and confirmed to be constant are not the same thing. Webb, with its ability to resolve absorption spectra in distant quasars at wavelengths not previously accessible from space, provides a new tool for these tests. And if dark energy is genuinely evolving in ways the DESI data hint at, the theoretical motivation for looking harder at variability in the fundamental constants becomes considerably stronger. On the biosignature front, the roadmap is perhaps the most clearly defined. Webb will continue to observe K218b, more transit observations at multiple wavelengths, using all 4 of its science instruments in a coordinated campaign designed to either strengthen or resolve the DMS signal. The community expects these observations over the next 2 to 3 years. If the signal strengthens, it will shift from a candidate detection to a probable detection, and the search for alternative abiotic explanations will intensify correspondingly. If it weakens or resolves into a different molecular identification, it will still have been scientifically productive. It will have sharpened our understanding of what biosignature detection actually requires. Beyond Webb, the Habitable Worlds Observatory is the planned NASA flagship for the 2040s, a large space telescope designed explicitly to image Earth-like planets around Sun-like stars and measure their atmospheric composition. It would be capable of detecting oxygen, ozone, methane, water, and potentially DMS or other biosignatures in the atmospheres of rocky Earth analogues at distances of tens of light years. The HW is not yet funded, not yet built, and not yet in the mission design review phase. But it exists as a congressional mandate and a scientific priority, endorsed in the most recent decadal survey for astronomy and astrophysics. It is the instrument that would, if deployed, and if life is present where it is looked for, not merely detect a candidate biosignature in a challenging spectrum, but image the alien planet itself, map its surface, watch its seasons change. That is not a near-term prospect, but it is a prospect. Within the lifetime of researchers currently in graduate school, it is scientifically and technically feasible to have in hand the definitive observational answer to the question of whether life exists beyond Earth. Not probable, not strongly hinted at, but confirmed or ruled out. Either answer reshaping everything, and MOM-Z14, that galaxy at the edge of cosmic time, formed 280 million years after the Big Bang, bright enough to register on a camera 13, 53 billion light-years away, and compact enough to fit its entire extent within a circle 240 light-years across. MOM-Z14 will not be the last galaxy to hold the distance record. Webb will find earlier ones. They are out there. Photons are arriving. And with each new record, the pressure on our models of early structure formation either intensifies or, if the models are adjusted correctly, resolves. But even the resolution will require adjustments. There will be new physics in those adjustments. There always is. Here then is where we are. A telescope at the edge of the solar system is reading the oldest light in the observable universe, finding objects no human instrument has ever seen before, detecting molecular signals in atmospheres 100 light-years away, and generating data that the most powerful theoretical frameworks our civilization has assembled are straining to contain. That is an extraordinary sentence. It is also an accurate one. We have not broken cosmology. We have not confirmed life on another world. We have not identified a new fundamental force or revised the laws of physics. What we have done is something that is, in its own way, more consequential than any of those specific outcomes. We have reached the edge of what our current understanding can account for, and we are standing there, looking at what lies beyond, with instruments capable of actually seeing it. The questions are real, the data are real, the uncertainty is real, and the next chapter of this story, the one that will determine whether these threads resolve into a coherent new picture of the universe, has not yet been written. It is being written now in the spectra of objects at the edge of time, in the atmospheres of worlds circling distant red stars, in the careful, methodical, relentlessly self-critical work of scientists who know that the most important thing is not to be right, but to be right in a way that cannot be argued with. That is the work, and it is underway.